Okay, welcome to lesson 4.2. We're talking about critical points and local extrema in this lesson. So remember that extrema is another word for maximums and minimums. So local extrema mean that there could be more than one minimum across a graph or more than one maximum, and we just look at those local kind of high and low points. A critical point, that's a new term. So for a function f at x, c is a critical number if when I plug the value of c into the derivative, I get the answer 0. Or when I plug the value of c into the derivative, I get an undefined result. And then if, of course, it's one of those ones that makes the value of the derivative 0, we can find the critical point by subbing it into the original function. Sometimes that'll work for when the critical number comes from the derivative being undefined, and sometimes it won't. So sometimes I'll ask you for critical numbers. That's just the x values. And sometimes I ask you for the critical point, and then you have to go back and plug that x value into the original function to find the y value. All right, so in our last lesson, we were making those charts, and we're going to use those charts now to find the maximums or the minimums on my graph. So we call this the first derivative test, and sometimes on your test, I'll ask you specifically to use this test. So we're under the assumption in this box that c is a critical number of f at x. So we've already figured that out. Now what we're going to look for is, does f at x change its sign? So this is the test that we're looking for. Does it change its sign? And the first one is, does it go from negative to positive at that point c? And so in my interval chart, I'll be looking at before the value of c, the interval before, and if it comes out as negative and the interval after comes out as positive, then that tells me that I have a local minimum on my graph. And vice versa, if I go from positive before the value of c in the interval to negative, the interval after c, then I'm going to have a local maximum. And you can kind of imagine what you've figured out here is, remember that the derivative tells you the slope of the tangent. So in this first case, we're seeing that the slope of the tangent is negative. And then it's all of a sudden switching at the point c, so this would be at the x value c, to a positive slope, and it's coming out like this. And you can kind of see that that's going to be the shape of a minimum on your graph. And then vice versa, in this one we're coming in at a positive slope, and then at point C, it switches to a negative slope. All right, so if f prime at x equals 0, and there is a local extrema, so if f prime at x equals 0, that means that the slope of the tangent, right? So this is just another way of talking about the slope of the tangent being equal to 0, and there's a local extrema, then it's going to look like a smooth curve at that point, and that's kind of what I've drawn in these two examples here. It's similar to the vertex of a parabola. I come in and I flatten out slowly into the point and then curve out of it. If f prime at x does not exist and there's a local extrema, then it's going to look like a cusp. And so that's more like the vertex of an absolute value function. So it could come in like straight lines like this, or it could come in curved as well. So it could come out like this. That would also be an example of a cusp. And of course, it could be a minimum as well. It doesn't have to be a maximum. Okay, let's talk about what happens when I have a critical point and it's not an extrema. So I might have a value of c. I find a critical point, a value of c that either makes the derivative equal 0 or the derivative is not defined. But I don't switch signs on either side of it. Maybe I am positive on both sides or negative on both sides. So what that would look like is here the critical point comes from the derivative being equal to 0. So that tells me I'm going to have that flat tangent point. And the derivative does not change sign. It's going to look like a cubic function from advanced functions. And I'm going to call this a safe slide. So the safe slide's got like this little flat spot. So you can imagine me like sliding down here. Here I am. And I come sliding down, and this kind of flat spot slows me down, and then I come down the rest of the slide. And so that's when I have a horizontal tangent in the middle. And you can imagine that, right? If I were to draw the tangent in here, it's going to be a horizontal line. Now, sometimes I'm going to have that the derivative does not exist, and the sign of f prime at x does not change sign at c. That's going to look like a sudden drop So if the derivative does not exist, it could mean that my tangent has a slope that is undefined. And remember from grade 9 math, when I have an undefined slope, it means I've got a vertical line, right? And so you can see that here at this point here, I've got this vertical tangent line here. So the derivative would not exist here. And coming in, the slope of this tangent is positive, and then coming out, the slope of the tangent is still positive. And so we're going to call this a scary slide. So I'm coming along nicely down my slide, and then all of a sudden there's this like drop. And then so I'm going to like hurt my bum when I land on this lower part and then slide down the rest. And then over here, I just forgot to mention that I did have a positive slope coming in and a positive slope coming out, so it did not switch sign. All right, so our algorithm for finding local maximum or minimum functions. So how are we going to go about this? First, we're going to find the critical numbers. So that means finding those C values. So I'm going to find the derivative. I'm going to figure out where does the derivative equal 0 and where does the derivative not exist. And I'm going to collect both of those numbers, just like we did in the last lesson. Then I'm going to make my sign chart. Again, I'm going to have rows. The top row will be the intervals of x and values between those intervals. The second row will be the test point. The last row will be the sign of the derivative. And then usually we do also have that row at the bottom for the behavior of f at x. Then we're going to use that first derivative test. I don't actually need to have this row technically for this question, but by the time we get to the test, sometimes we'll be using the chart for multiple things, and then I'll want to include that row. So we're going to use the first derivative test to determine whether the critical number is a local maximum or a local minimum. And basically all that means is I'm checking to see if they switch sign. Now, if the question just asks me for the critical numbers, then I will already have those values. But if the question asks me for critical points, then I'll go ahead and find the y values to go with that, and then I'll put it all together in a summary sentence. So let's try a couple of examples. I've got 4 different examples here because I want to make sure that you see all the different types of graphs that might pop up. So the first one, you might recognize this is a quintic function, so we looked at stuff like this in advanced functions. So we're already pretty familiar with what this graph is going to look like, but we're going to use all this calculus now to help us find all the important parts. Part I asks us to find the critical points for each function, and then use the first derivative test to determine whether the critical point is a local maximum, minimum, or neither. So for question A, part I, we're going to find the critical points, which means I need to find the derivative of this first function. So right now I'm focusing on this guy here. And taking the derivative, I bring the power down and subtract 1 from the exponent. And then it's just a sum or difference, so I can just take the derivative separately. Taking the derivative of the second part is just -5. So now I've got my derivative. I want to figure out where does it equal 0 or where is it not defined. So first, f prime at x is equal to 0. And this is equal to 0. So I'm going to rearrange and solve this. You can try to factor it if you want, but when there's only one term with an x in it, you can isolate no matter what the exponent is. So I get x to the 4th equals 1. Don't forget, whenever you have an even exponent and you bring it over and change it into the 4th root here, you need to have a plus minus. I didn't leave myself a lot of room here. There's a plus minus in front of that. And so it's just plus or minus 1. So I got 2 critical points, or sorry, critical numbers from f prime at x equals 0. I also need to check where does f prime at x not exist. And this derivative here is a quartic function. So this is a polynomial function, and I know that the domain of a polynomial function is the set of real numbers. So f prime at x always exists. And then I can go ahead and set up my interval chart. So across the top, again, I'm starting at -infinity, and I'm going to stop at -1 and at +1. So -1, So I just have to go through them in order, right? I have to go from smallest to biggest. All right, we're going to pick a test point. We're going to figure out what is the sign of the derivative. We just need to know about those positives and negatives because we want to see if they switch sign. And then we can add an extra row here. Now this question does not require it because it hasn't asked me about intervals of increase and decrease. So I am actually going to leave it off here because they're not asking me about it. But if a question asked me about intervals of increase and decrease, I would include it so that I could come up with my therefore statement. All right, so I'm picking some number between -infinity and -1. It does not matter which number you pick. You're going to plug it into the derivative up here. So I'm going to pick something really, really big, like a really big negative is what I mean. So really, really small, I guess. I'm going to plug it in here. When I raise a negative number to the power of 4, an even power, it becomes positive. And so it's actually huge, right? Now I've got 100 to the power of 4 times 5. That's a huge number, and I'm just subtracting 5 from there. So this is going to end up being a positive. And if you're not sure, of course, you could type it into your calculator. For -1, I do not need to pick a test value. There's only one number. And then I'm going to remember that -1 gave me the value of 0 for my derivative. And then moving into this interval here, you'll probably pick 0. Remember, you can't pick -1 or 1. You could pick a half or -1/2 or a quarter if you like. I'm going to plug 0 into my derivative function here. So I get 5 times 0, that's 0, minus 5, so that's negative. And then again, when I get to 1, I don't need to pick a test value. This gave me the value of 0 for my derivative. And then picking a number bigger than 1. Again, you could pick something, you could pick 2 if you like, or you could pick something comically big here. Sometimes it actually makes it easier to do the math. So if I pick 1,000 and put it in here, 1,000 raised to the power of 4. It's a huge number times 5, so a really big number. And I'm just subtracting 5 little pieces, so that's positive in that interval. So this question just asked me to use the first derivative test. This is the only piece of the chart that I need, and all I'm looking for first derivative test is did I switch sign as I moved from one interval to another, realizing that these guys here are critical numbers. So I'm looking on either side of those critical numbers. So what I can see here is I do switch sign at -1, and I switch sign again at +1. This question, though, did ask me for the critical points. So that means I do have to find the y values at each one of those critical numbers. So I'm going to find the y values since they asked for points. If they just asked for critical numbers, I would move on and just write my therefore statement. When I find the y values, or the point, I need to plug each of these critical numbers into the original equation. So I'm going back up to x to the power of 5, so -1 to the power of 5, minus 5 times x, all the way up to the equation given in the question. And so I get -1 plus 5, or 4. And then I'll do the same thing with the other. This time I get 1 minus 5, so I get -4. And so what I figured out at this point So I'm summarizing here. I'm going from positive to negative at x equals -1. And I'm remembering that the first derivative test back here told me if I go from positive to negative, then that's going to be a local maximum on my graph. And hopefully you don't like memorize this. You can just kind of think about a positive slope heads up and a negative heads down. And I kind of just cup my hands in front of my face to remind myself that that's a maximum. And here I'm going to write the point because that's what they asked for. So when x is equal to -1, we found that the y value was 4. Now, in this therefore statement, I do need the first part of this statement because that's what shows me that you used the first derivative test. This part of the statement right here. Later on in this chapter, I'm going to teach you another way to find the maximums, and so then there'll be a different statement here to tell me that that's where you came up with the conclusion. So next I'm moving on to the next part of my graph, or my table here, where it goes from negative to positive. And so here I've got a negative slope, so I'm heading down, and then all of a sudden I'm heading up at the positive slope, and so I can see that that's going to bottom out at a minimum. And again, when we had the x value of 1, we came up with the y value of -4. Okay, so that's part I in the question. Part I asks us to find the x and y intercepts of the function and then sketch the curve. So to find x-intercepts, if I'm on the x-axis of my graph, then I don't have a height, right? I haven't gone up or down. So it means that the height is 0. So we set the y value equal to 0. And again, here we're talking about the graph. So we're talking about the original function. So I'm going to take, instead of f at x equals, it'll be 0 equals my equation. And now I'm going to try and solve this. So I'm going to factor out a common factor of x. Now I can't just divide away an x. This is part of my solution. So once I have it equal to 0, I'm going to set each factor equal to 0 and solve. So either x equals 0 or x squared equals, or x to the power of 4, sorry, equals 5. And then I can solve this one. And because I'm going to sketch the graph in this question, I do actually want to know what this is numerically as a decimal, and I get about 1.5. And now we need to find the y-intercept. Again, if I'm on the y-axis, that means I have not moved left or right on my graph. So it tells me that the x value must be 0 on the y-axis. So I set x equal to 0 in my equation, and I get 0, which we already knew from over here that that was going to happen. So now we're going to put this all together and draw a sketch. I'm going to do a rough sketch at this point. Later on in the chapter, we're going to build more details, and then I'll do a more detailed grid for my graph. What I know here, I'm going to add each of these points that we figured out. So I've got the y-intercept, which is also an x-intercept, and then I have an x-intercept at negative 1.5 and an x-intercept at positive 1.5. I'm going to label my x and y axes, and I'm labeling all the relevant numbers. Eventually we'll put this all together on a grid later on in the chapter. The other thing I'm going to add now is I know that I have a maximum point at -1, 4. So I know that there's a maximum point here, and at 1, -4, there's a minimum. This gives me an idea of what my graph looks like. Now, those are the only maximums and minimums. You can be confident because of the work that we've done here that the graph does not turn around. It simply goes like this. Well, trying to get there on my tablet. That should be a smooth curve. That's not pretty. Let's see again. That's a little better. Okay, so I know that even though this is a power of 5 function, remember we did start with an x to the power of 5, and that can look like this. It could have 4 kind of humps in the graph, but this one behaves more like a cubic function is what's happening here. And that's okay for quintic, you might remember from advanced functions. All right, moving on to equation B. I'm just going to copy it down here so that we've got it. So the question started. like this. Okay, now the first thing that they ask us for in part I is to find the critical points of the function. So we're going to start by taking the derivative of this. All right, now once we have the derivative, to find the critical points, we're going to figure out when does it equal 0 or when does it not exist. So I'm going to set it equal to 0 and solve. And before I forget, I'm just going to talk about the fact that this derivative here is a polynomial function. So I would say that a polynomial function is really obvious that the derivative always exists. So you can just write that. This won't always be true. You will sometimes have to look, but my reasoning here is since it's a polynomial. All right, so I want to know where this thing equals 0, so I'm going to factor, and I see here that there's a common factor of 12x. And then I have a remaining quadratic in here. It's a simple trinomial, so I know that when it factors, I'm just going to get two brackets with x's at the front. Simple trinomial because the coefficient in front of the x squared is 1. And then I'm looking for two numbers that multiply to 4 and add to 4, so they're positive 2 and positive 2. Or you could write that as x plus 2 all squared instead of writing the bracket twice. Now I want to know where this equals 0, so I'm going to set each of these factors equal to 0. You don't have to do it twice when the bracket matches, right? Once you do it once, you've got it. So here I get x is equal to 0 or x is equal to negative 2. I've got my two critical numbers, so we're going to make our chart. Again, starting at negative infinity and just going along and stopping at each of our critical numbers. Then we'll pick a test point. And we'll find the sign of f prime at x. So when I'm doing this, I'm looking at the derivative function. So whenever you look at the derivative function, you've done some simplifying along the way here, but we didn't actually move anything across the equal sign. So it tells me that I can use any one of these versions of the derivative to help me out here. So I'm going to use this bottom one. This is where I'm looking when I'm figuring it out, but if you prefer to look at the double bracket, then you can do that. I think that the factored version is the easiest to look at. So I'm going to pick some number between negative infinity and negative 2. I'm going to pick negative 10, but you can pick negative 3 if you like. So when I multiply this, or sorry, when I substitute this in, I'm going to get 12 times negative 10. That's a negative number, so I'm kind of using that factoring idea that I used in the last lesson. And then I'm plugging negative 10 into this bracket. It's going to give me negative 8, so a negative number, but it's squared. And then I imagine multiplying these three negatives together, and that would result in a negative overall. And then at negative 2, we came up with negative 2 because that's what made the derivative equal 0. And then I'll pick a number between negative 2 and 0, probably negative 1. I'll plug negative 1 into the first factor. 12 times negative 1 is negative 12. And then plugging negative 1 into the bracket, I get a positive this time, and I'm squaring it. So altogether, I have a negative times a positive times a positive. That's overall a negative. We came up with 0 because it made the derivative equal 0. And then picking some number between 0 and infinity, I'll pick 10. Again, you could pick 1 if you like. I'm going to do 12 times 10, that gives me a positive. And then plugging 10 into the bracket, that's also going to be a positive squared. And so here I'm going to get positive times positive times positive. That is a positive. So we've got our three answers here, negative, negative, positive. You can add that extra row across the bottom if you like, but in this question they didn't ask me about intervals of increase and decrease, so I'm going to skip that part and just go on to stating my critical points. So I know that I do have a critical point at -2, even though it doesn't switch sides. So I know that it's not a maximum or minimum. It is still a critical point. So I'm going to go back to my original function and I'm going to plug -2 in. And I get a height of 16 for that point. And then plugging into my original function 0, they all have an x, so I'm actually going to get 0 plus 0 plus 0 and a height of 0. And then we'll write up our conclusion. So again, we have a flat point at -2 because the value of the derivative is 0, but the slope coming in was negative, and the slope coming out is also negative. And so I'm going to see that kind of safe slide at that point. So there's no extrema there. It's not a maximum or minimum. So here I'm going from a negative slope, so heading down, and then all of a sudden I come up and turn up. So that's going to be a minimum point. And again, I grab my y values from over here. All right, so that's part I. Now in double I, it asks us to find the x-intercepts. Again, I'm going back to the original function here. I'm going to try to factor this and come up with all the different x-intercepts. So I see that there's a common factor of x squared. I'll pull that out. And then I can set each one of these factors equal to 0. You could continue trying to factor here, or you can pull it off to the side and factor from there. So I'm going to separate it at this point. Again, I don't have to worry about the squaring here. It's just x equals 0. Or if you want, you can say x squared equals 0 and then take the positive and negative square root of 0. It's 0. All right, so then the other piece is that this parabola, I want to know where it equals 0. Now, when I have a parabola with all positive coefficients, I'm a little suspicious here about whether or not it has x-intercepts. So I know that this parabola opens up. I just don't know. It also kind of looks like it might be shifted up. I'm not sure because it's not in vertex form. But one of the ways I can check is just by looking at the discriminant part of the quadratic formula. So the discriminant is the piece that's underneath the square root in the quadratic formula. And we know that we can't square root a negative. So what I want to know is this guy negative? If he is, then there are no answers here because I can't square root a negative. So we'll check it out. And what I get here is a negative number. So you can type that into your calculator if you're not sure, but this guy here is less than 0. And that tells me that there are no solutions for this piece of the equation. So I have one x-intercept at x equals 0. That tells me that the y-intercept should also be at 0, 0. Otherwise, you don't have a function if you have more than one y-intercept. And when I plug it into my original equation, right, I'm going to get 0 plus 0 plus 0, which is 0. So I've got my, my x and y intercepts. This function only crosses through each axis once. I'm going to draw a quick sketch of this. function, and I'm going to also include my critical numbers on that sketch. Oops. There we go. Okay, so we know that there's an x-intercept and y-intercept here at 0. I'll label my axes. I also know that there is a critical point at -2 and 16. I'll put that a little lower actually so I can see above it. I get to kind of play with the scale because there is nothing else. There's no grid, so I can kind of just move things around. I know that there's a critical point here, so I'm going to put that in, and then we'll add what we know. So I know that before -2, the slope values are all negative, and then I flatten out at 2, right? That's what this 0 here is telling me, it's flat. So again, I must flatten out at 0, and then come back up. I have a positive slope over here, so these guys are kind of connecting. And this is what my graph is going to look like. So I know that I have a minimum point at 0, 0. I could start there. There's my minimum. And after that, there's no important value, so it must continue to go up. And then I'm going to come up into my other critical point. Before this critical point, I have a negative slope. It flattens. Make sure I can tell on your sketch that there is like this tiny flat spot here. So you may need to exaggerate that. And then it comes out as negative as well afterwards. All right, I'm going to stop the video there, and then we'll come back for C and D.